In this lecture, we're going to start looking at classification, but we're going to use as an example for a linear classifier, logistic regression, which in a sense is also a regression. This will help us understand better the difference between regression and classification. So I'm going to talk first a bit about the idea of classification, linear separability, when we can use linear models to separate our classes, and then we'll look at logistic regression as a classifier and how we can solve the problem again of going beyond linear models using those transformations, nonlinear transformations to higher dimensions, as we saw with regression problems. So let's start with the classification and the idea of separability. Consider these two classes of points. The values here on the two axes are measures of the expression of two different genes, and these points marked in blue are the values of the expression for normal cells, and these in red for tumor cells. And we can see here when we use these coordinates, so these values of gene expression, we can create a straight line that separates the two classes, the normal cells and the tumor cells. So when this happens, when we have a linear separation between our classes, in this case in 2 dimensions it would be a line, but if we generalize for an arbitrary number of dimensions it would be a hyperplane, but in any case a straight, a linear separation. If we can do this, then the classes are linearly separable. And so we can use a linear model to separate our classes. The frontier that we have here, in this case, it's a linear discriminant. It's a discriminant because it separates the two classes, and in this case, it's linear. It's a straight line here in 2 dimensions. In some cases, it may happen that the way the classes are distributed makes it impossible to separate them with a linear discriminant. In this case, we have this blue point here and these red points here that make the frontier a curve, and so we cannot draw a straight line here and separate the two classes without errors. Okay, so the idea here in classification is to try to separate these two classes. We saw with regression that we defined some hypothesis class. We chose some hypothesis class. We have this, for example, this model for a straight line. And then with the parameters, we choose which line we want to use. And the idea would be to try to approximate as much as possible the data that we have. But in classification, we need something else, because if we want to use a line to separate the two classes, we need to be able to specify which class is on which side of the line. So there is one side for the blue class and one side for the red class in this case. So we need some additional information here. If we generalize this for n dimensions, we will have a hyperplane. So in 3 dimensions will be a plane, in 4 dimensions and so on. And we can define a direction for one of the sides of the hyperplane and distinguish that from the other by using a vector that is perpendicular to the plane. So you can imagine here, for example, in this line, we could use a vector pointing towards the blue class, and this would tell us which side is the blue class, and the other side would be the red class in this case. So this way we can define the discriminant as with this expression. We have this vector that is perpendicular to the hyperplane. This, the inner product of this vector with the features that we have for some point plus this constant. If this is 0, it means that this point is falling exactly on the discriminant. If this is positive, then we are on one side of the discriminant, the side pointed to by this vector here. If it's negative, then we are on the other side. So this x would be an n-dimensional vector that has the features that we are using. For example, in this case, it's a 2-dimensional vector with the expression values for 2 different genes. These would be the features we are using to determine the classes for our points. So this is an example in 3 dimensions. The x value would be a vector of these 3 dimensions here. This perpendicular vector would be this one, this red one that is perpendicular to the plane. And this constant basically determines the position of the plane. But this vector determines the orientation of the plane. So this way, if this expression is 0, it means that the point defined by these coordinates is falling exactly on this plane. If this expression is positive, then the point is on this side of the plane where the vector is pointing to. If it's negative, then it's on the other side of the plane. So with this expression, we can find a way to not only create the discriminant, the linear discriminant. This is the plane where the value of this expression is 0, but we can also distinguish between two sides, the positive side and the negative side. And this way we can separate the two classes using this discriminant. Okay, so given this function, y, that is a function of the inner product of this perpendicular vector and our coordinates plus this constant, we know that it is positive on one side and negative on the other. So if we have the parameters here, all these w and w0, we have our discriminant, and we can separate the two classes. One is the positive one and the other is the negative. Now the problem is how we find the best discriminant. So let's start with the wrong answer. What I'm going to tell you now is not the correct solution, and we'll see it gives us the wrong result, but it's important to understand the difference between regression and classification. So remember, with regression, we used this quadratic error and tried to minimize the difference between what we were predicting and the target value. So we can now do something similar. Let's suppose that this is predicting the class. So this is positive on one side, negative on the other. We can attribute these values, these labels to the two classes. So one class, the positive one, has a label of 1, and the other, the negative one, has -1. And now we consider that this is simply trying to approximate the class labels, 1 and -1, and we minimize the quadratic error. So the reasoning is the same as we did for regression. In regression, we wanted to predict some value, so we minimize the quadratic error. Now we want to predict a value, which is the class label, 1 or -1, and we try to minimize the quadratic error too. So basically, we're going to find these parameters here that minimize the square of the difference between the prediction that we have on this function, which is negative on one side and positive on the other, and all the class labels of the examples that we have. So let's start with our data. This is the data on gene expression, these two genes, carbonic anhydrase and guanylate cyclase activator, and we have the expression of these two genes in these relative units here on the first two columns, and then we have this label 1 or 0 to indicate whether this cell is a tumor cell or it's a normal cell. So what we're going to start by doing is to rescale this so that we have everything close to around 0, between -1 or 1, something like that. So remember this problem we had on the previous lecture to avoid having, for example, very large numbers and then very small numbers, because this can give us problems with numerical stability when we are trying to fit our models. So two different ways of rescaling can be normalization. Normalization squeezes everything to a range between 0 and 1. And the way we do this is we obtain a new vector by subtracting the minimum of all the values. From each of the values, we subtract the minimum, and we divide by the difference between the maximum and the minimum. So this brings everything to a range between 0 and 1. An alternative is to use standardization, which involves subtracting the mean from all the values and then divided by the standard deviation. What this does is that it rescales the values that we have into a set of values that has an average of 0 and a standard deviation of 1. So it falls mostly around 0 and mostly between -1 and 1. So one important thing is that in real applications, we should store these scaling parameters so that we can apply the same rescaling to new points, and we can do the reverse transformation when we want to predict something, for example, in the correct units when we're doing a regression and so on. But we need to store these parameters. So let's do this here. We're going to load our data. This is simply to load the data in the text file into a NumPy matrix. And now we're going to separate the class labels. The class labels will be the last column. And these parentheses here are just a trick to preserve the dimension of the matrix. So this will still be a two-dimensional matrix, only it will have a single column. If we do it like this, then we have a one-dimensional vector, because this is only a single column, and NumPy will give us just a one-dimensional vector. So this way we keep the same shape of the matrix. We separate the target labels here. We are not going to rescale the target labels because the target labels are just zeros and ones. In regression, we usually rescale the target value, but that's because it's a continuous value that is in some arbitrary units. Now we're going to separate the X values, which are the features, what we input into the model to make our prediction, and we're going to rescale the features. Basically, we're going to compute the means in the direction 0, the direction of the rows, and the standard deviations for all the columns, and then we're going to rescale like this. So these vectors will have two elements each. This is the mean of the first column and the mean of the second column in this vector, and this is the standard deviation of each of the columns. And by doing this operation, NumPy will broadcast it over all the rows of the matrix of X's, so we can do this in the single instruction and rescale our features. Okay, so one thing we can do, this is not mandatory, but you will probably find this a lot in the literature, is instead of having this ugly expression here, where we have a set of parameters for the vector with the orientation of the plane, plus an independent constant here, we can do this trick. We can put these together, all of these parameters and this constant, we put them together in the same vector. Let's call it tilde W. And now we're going to add a 1 as an additional feature to our original X. So it's all the features that we have plus a 1 at the end, and we call this tilde X here. So if we do this, we can write the exact same expression just with this inner product, because this extra constant here will just multiply by 1 when we are doing the inner product and add to the rest. But this simplifies the expression and makes it a lot cleaner if we have to write the code or to use the expression and so on. So we can easily do this, create a new matrix with an additional column and just fill it with ones, so it has ones everywhere, and just copy the original X to the first columns. So the last column is still left at 1, and the others have the original X, and this way we create this X tilde. So now we can put everything, all the parameters in the same vector, and just deal with a single vector with the parameters, instead of, for example, having extra arguments for the constant and so on, which could be a bit messy for the writing the code. Okay, so now we need the cost function. Remember that what we're trying to do is create or find the set of parameters that will give us this expression in a way that it will provide output a -1 for the negative class and a +1 for the positive class, or as close to as possible to that. And for that we're going to minimize the quadratic error between the prediction and the class label that we have. So this is what we're going to do this. We're going to create the cost function. This theta will be just a parameter, so the W vector with all our parameters. This is the matrix with the features, what we input. So actually this expanded matrix here that includes the last column of ones to simplify the expression there. And the Y is the class labels. Now there is one detail here, and sometimes you have to think about this. It depends on the actual code that we're using, so you need to check what is expected for the class labels. but note that we are considering that the class labels would be 1 on one side and -1 on the other. However, our data has class labels of 1 and 0, and this would not work like this. So we convert them to 1 and -1 by doing just this small operation here. So 2 times the label -1. If the label is 0, then 2 times the label is 0, and this turns to -1. If the label is 1, then 2 times 1 is 2, -1 is 1. So this just converts the 0 into -1, and the 1 keeps at 1. So now we just compute the cost by computing the dot product, the inner product between the features and the parameters that we have here. So basically it's this expression here. And now we compute the quadratic error of the difference between the values that we predict for all the examples and their corresponding classes. So here we are computing this expression for the quadratic error. So this means that we're trying to now find the parameters that best approximate this. In order to do that, we need to minimize this error. So we can just use, for example, the minimize function from SciPy Optimize from this library. You have these installed. If you're using Anaconda, as I suggested, you have these libraries installed by default. And so we load the data, expand the features, and now we are going to start with an initial guess of values 1 for all of these coefficients. And this is the starting point. And now what minimize does is try different variations of these coefficients in order to minimize the function we present here. And to call this function minimize, we give it the name of the function we want to minimize. So this is the cost function that we have here. We give it the initial guess for the coefficients. In our case, it's just a vector of ones of the right dimension. And what arguments the minimization function needs to send to the cost function to minimize, in addition to the vector with the parameters it's trying. So the function receives the parameters first, and then, in this case, x and y to do compute the predictions and compute the error. And so we have the coefficients here, and then as additional parameters, we give this tuple with the x and the y's. This tolerance factor here is just to specify when the minimization stops. So when it gets stuck and doesn't improve by more than this small value, it stops and outputs the result. So the result will be on this optimization object. The optimization results object has this x field with the final the best coefficients found. There are other attributes here for the final error, the number of iterations, and so on, but this is the one that matters for us. And this will allow us to find the coefficient, so this W here, that specifies the discriminant that we want. So doing this minimization, we get the discriminant. I'm going to skip here some geometry parts because remember, we are getting the vector perpendicular to the discriminant plus that additional constant. If we want to actually plot the discriminant, we need to compute a perpendicular vector and so on, but I'll skip that part, it's not very important. The important thing is to look at where the discriminant lies. So this is the result that we got, and it's obviously not a good result. It should be easy to separate these two classes. It's obvious that it should be something aligned somewhere around here, but we got a line over here. And the reason why we got a line over here is that when we are minimizing the quadratic error, we are trying to pull our line as close together to the points as possible. So it needs to put all of these points at 1 and all of these at -1, but we have a quadratic function here, and as the function increases, the error increases between between the function that is increasing here and the values that we have. When we square that, we are starting to have a huge weight on the error of these points that are far away. So since the greater the distance to the discriminant, the greater the predicted value, and since we are squaring that difference between the prediction and the actual point. This makes it that the points that are far away pull the discriminant with lots more force than the points that are close together. Now, this makes sense in a regression, because if we are doing a regression, we want our line to go as close as possible to the points. And so if points are very far away, they must pull the line strongly so that the line moves closer to those distant points. But when we are doing a classification, we don't really care about the points that are far away. What we care is about the points that are close to the discriminant. Those are the important ones. The others, as long as they are on the right side, it doesn't matter. It's these points here that we should really take care to separate properly, because once we separate these ones, all the rest come for free and we don't need to concern about those. So the reason for doing this wrong first, using the same reasoning as we used for regression, is to help you understand this big difference between regression and classification. Even though in both cases we are fitting the parameters, trying to minimize a continuous function, the error function, the loss function that we're trying to minimize, the objectives are different. In the regression, we want to fit the data as closely as possible. So we need our hypothesis to output predictions that are close as possible to all the points. But in classification, we want to separate our data into different classes. So we really must focus on the frontier and not pay too much attention to points that are far away from the frontier, as long as they are on the correct side of the discriminant. Okay, so let's look at logistic regression and see how we can create a classifier, even though it's in its inner workings, it's still a regression. So let's assume there is a function g, that inputs the features that we have, this x vector, and that has some parameters we can adjust. And this function gives us the probability of the point described by those features belonging to class 1. So this is the function that we want to approximate, the function that tells us how probable it is to find a point belonging to class 1 at that position, at those coordinates x here. And we can adjust these parameters to try to fine-tune these probability predictions. Now, the discriminant, the hyperplane that separates the two classes, ideally should be on the position for which the probability of belonging to class 1 is equal to the probability of belonging to class 0. So the idea is that points on this side have a higher probability of being in class 1, points on this side have a higher probability of being in class 0, but somewhere here in the middle we have exactly the same probability of being class 0 or class 1. So that would be where the discriminant is, where the two probabilities are the same, or where the probability of belonging to class 1 is the same as 1 minus the probability of belonging to class 1, because this would be the probability of belonging to class 0. We only have these two options. So, based on these features, if we assume that our function gives us an approximation of these probabilities, and that's what we're trying to do, then at the hyperplane, the logarithm of this fraction, the probability of belonging to class 1 and 1 minus the probability of belonging to class 1 should be 0, because these two should be the same. So this fraction here is 1 and the logarithm of 1 is 0. Since we have this function approximating here, we know that this function should have this characteristic. At the discriminant, the logarithm of this fraction should be 0, because the fraction should be 1. In addition, we want the function to be a probability, so it must vary between 0 and 1. So if we do this, if we put in these conditions, we know that the logarithm of the function and 1 minus the value of the function must be 0 at the discriminant, and we also have a linear discriminant. So a linear discriminant can be described like this, or we can just put the W tilde there, because this one includes, the W tilde includes not only the perpendicular vector but also the constant there. So basically this is what happens. We need our function to be behave like the linear discriminant here. This is 0 at the discriminant, this is 0 at the discriminant, and if we impose this constraint, we find that this must be the shape of our function. So if we use a function like this, we can create a function that approximates the probability of belonging to class 1 and have this property that the logarithm of this fraction, the probability of belonging to class 1 divided by the probability of belonging to the other class, class 0, will behave exactly as the function we used for the linear discriminant. It's 0 when the probabilities are the same, it's negative on one side, positive on the other, and follows the same progression here. So it has the same values as the expression that we used for the linear discriminant. So in order for this to work, this must be the function that we're going to use. 1 over 1 plus e raised to minus this expression here for the discriminant, which includes the parameters and the point that we are using. So if the point falls exactly at the discriminant, this is 0 here, and we have a 0 at this expression, right? 0 here. So basically we have a 0 on this expression here. And we have the point falling exactly on the discriminant and having the same probability on one side and the other. Okay, we get when this expression is 0, then this fraction here will be 1 and the logarithm will be 0. So what we have in this case, in this function, is a function of this shape. This is the logistic function, the function that we have here. It varies from 0 to 1, exactly as we wanted for the probabilities, and it has these characteristics of retaining the discriminant where the probability of belonging to one class is the same as the probability of belonging to the other. Okay, so another thing that helps us understand why this is more useful is that with the quadratic curve that we had for computing the error, we use, when we go away from the frontier, from the discriminant, the points start weighing more and more. So we start to have a bigger weight for the points that are far away from the discriminant than for the points that are close to the discriminant. The logistic function solves this because we have the 0 here. This falls down to 0 or goes up to 1, but then it levels off. So the points that are close to the discriminant, it makes a difference if they are closer or further away, but points that are too far away for either side are not making any difference to the value of the function, because these will be 0 or very close to 0, and these will be very close to 1, no matter if they move a bit more or a bit less. So when we're trying to optimize this kind of function, those points that are away from the discriminant will not have much weight unless they are on the wrong side. In that case, we will have a difference between the predicted probability and the actual class that they have. Okay, so now how do we find our parameters? Again, by maximum likelihood. We're going to use the same approach as we did in linear regression. We're going to consider that if we have a function with some parameters, we are estimating that the probability of each point belonging to its class can be computed in this way. So if point belongs to class 1, Tn is 1, we can use the estimated probability that comes from our function, and this gives us the probability of belonging to class 1. If it belongs to class 0, then this is a 0, and this expression here will be 1. Anything raised to 0 is 1, and so we can ignore this and use this side. This side is 1 minus the probability. So this is the probability of belonging to class 0, and it will be used when t is 0, because we are doing here 1 minus 0, so this raises to 1, and we use this value here. If the point belongs to class 1, then 1 minus 1 will be 0. We can ignore this part here, and we use the probability of belonging to class 1. So we can do this for all the points, and basically multiply the probability we are assigning to the point belonging to the class it actually has. So this would be the probability of having our data assigned to those classes if we assume our function to be giving us the right probabilities. So as we saw before, the likelihood of our parameters is the probability of the data assuming the parameters are correct. And now we're going to change the parameters to maximize the probability of the data if the parameters are correct. We can take the logarithm as we did before. So the logarithm of the likelihood would be, we would change all of these to the product to sum, then use the logarithms there. The exponents here will turn into multiplication. So basically this is the expression for the logarithm of the likelihood, and maximizing the likelihood is the same as maximizing the logarithm. And so we use this expression because it's a lot neater, a lot better to optimize. We don't have problem with overflows of the numbers for all these multiplications or these exponents here and so on. It's just the sum of these expressions. So if we want to maximize the likelihood, we want to minimize the cross entropy or the logistic loss, which basically we change the sign here. We can divide by n to get an average for all the points, but this is a constant. It doesn't make much difference. And so this would be our loss function. Our error function would be the logistic loss or cross entropy, which is this expression here. And our function is the logistic function that will depend on the parameters and, of course, on the coordinates of the points. So this is what we're going to do. We're going to try to change these parameters, adjust these parameters in order to minimize this expression here, the logistic loss. So let's see an example first with linearly separable data. We can write auxiliary function just to compute the logistic function. So this is this function here. We get some x inside and we output the value for the logistic function. So it's just 1 over 1 plus e raised to minus x. Note that this writing it this way using NumPy, this can be a single value or it can be a vector of x's, because NumPy will automatically broadcast this and return a vector with all the logistic functions computed for the different x's we give. Okay, so now here we create the cost function. We receive the coefficients. These are the these w's here all together, and we receive the x values, the coordinates of our points, and the y, which are the labels for the class. The labels in this case are 0 or 1. So now we use the we create a vector of coefficients that is a column vector for this, so that we can use the dot product to multiply all the rows of our matrix of x with the coefficients that we have that are now a column. This sometimes can be a bit tricky, but you just need to remember the rules for these algebraic multiplications between matrices and vectors and so on. If things work incorrectly, you'll probably have an error because the matrix dimensions do not match. So just check if you need to put one before the other, or if it needs to be a row or a column, but you probably can just do it a bit on paper to figure out which way you need to do. But in any case, we are not going to work too much at this level of detail. I'm just showing you this code so that before we start using the actual libraries for logistic regression and so on, you understand the details of what's happening. So now we can create this term here. So this first term here, we multiply the class by the logarithm of the output of our function. So if the class is 0, this one disappears. If the class is 1, we use this value here. And the other is the same thing, but 1 minus the class. So basically, this will be used for all points in class 1 and this will be used for all points in class 0. And so that's what we can compute here. The ones for class 1 are just the logarithm multiplied by the class, and the ones for class 0 are, we use 1 minus the class, and we have 1 minus the values that we got for the logistic inside the logarithm there. Okay, so now we just compute the mean of these. Remember that these are vectors because we are using these for all the values in one go. We don't need to create a loop to do this sum here because NumPy just broadcasts all these operations and creates the vectors with the results. So we just compute the mean for this vector, the sum there. We change the sign, and this would be the cost function that we need to optimize. So when we minimize this function, instead of the quadratic error, we now get a much better result. The reason for this is now that the logistic function is rising on this side and then leveling off, and then lowering on this side and then leveling off. So as long as the discriminant falls somewhere here between these points, everything works fine for the two sides there. So this is to illustrate this important difference between regression and classification, in that in classification what we really care about is separating the points that are close together here. Those points that are far away on the right side, we can just ignore them. Logistic regression is a regression because we are trying to approximate these probabilities, which are continuous. So we're actually trying to do a regression. We have a different loss function because when we do the maximum likelihood, we are not doing like in linear regression where we assume a normally distributed error on the target value, but rather we are considering the probabilities of belonging to each class. So we get a different loss function, but note that the approach, the reasoning is the same. We are trying to find the parameters by maximum likelihood. But we can use this regression as a classifier because we draw the discriminant at the hyperplane, at the division line, where the probability of belonging to class 1 is the same as the probability of belonging to class 0. So we are doing computing a regression that gives us a high probability of belonging to class 1 on the side of class 1 and a low probability on the side of class 0, but then we draw the line at the midpoint where the probability is 50-50 for each side. Okay, so now let's see the problem that we have when the classes are not linearly separable. Consider this example. We have a blue point there and some red points sticking out over here. We can compute a straight line that optimizes, that minimizes that loss function, but this will not give us a correct separation between the two classes because it's not possible to separate them with a straight line. So we're going to do the same thing that we did for linear regression, and we're going to expand the features non-linearly. So we're still going to use a linear model, but at a higher dimensional space after a non-linear transformation of our data. So let's do this. Let's increase our features by adding the product of the two features. The two original features are these gene expressions. This is what we are using as input to try to predict the class. But now we're going to create a new matrix with an additional column. We're going to copy the value of the original matrix to the first set of columns, and the last column we are just going to put the product of the two coordinates of the first and the second column in the original matrix. So what we have would be this gene expression, and the product of the two gene expressions. And now we're going to use logistic regression. I'm not going to use our implementation, which was just for illustration to show you the details. In practice, you go to the linear models module in scikit-learn and you use logistic regression. So you just create a logistic regression object. This is a regularization term. The larger it is, the smaller the regularization. We're going to look at this in more detail later on, but if you use a very large value, then this means we are not using regularization practically. This is again just the tolerance factor for ending the the optimization, and now we call fit this method to adjust the parameters to our data. So this is what you do when you use these models in scikit-learn. You call fit to adjust the parameters, and we give the matrix with the attributes, the x values, and then we give an array with the class labels. So in this case, we will use logistic regression to try to find this linear discriminant, but now we're working in a three-dimensional space because we have the two original coordinates for the gene expression plus an additional coordinate, this z-axis here, which is the product of the two initial features. So we can see that the data points that we have are now spread out on a surface that is slightly bent because we did this nonlinear transformation using the product of the two features. And because the surface where they are now spread out is slightly bent, when we separate them with a linear discriminant, which is this plane that we computed here, the actual intersection with that nonlinear transformation that we did will be a curved line. So this is basically the same thing that we saw with linear regression on the previous lectures. We can do more. We can not only add the product of the two coordinates, but also expand with the square of the first one and the square of the next one, of the second one. Note that this is still the same data originally. We are just expanding this into 5 dimensions, and we are bending this hypersurface where our data is spread out, because these are nonlinear transformations. And so when we do a linear classification on this higher dimensional space, we get something that is more bent in the original 2-dimensional space when we consider only the first 2 coordinates. So when we can keep doing this like we did with linear regression, we can just keep adding different terms for this polynomial expansion, and so now we can increase the ability of our discriminant to bend in the original dimensions, noting that we are always doing a linear classification in this extra dimensional space after the nonlinear transformation. Okay, so eventually we start getting strange results like this. For example, when we do this expansion, our classifier predicts that points falling over there will belong to the red class. So this is a bit strange. It's very suspicious. It's not doing any error on the training set, but this probably is not generalizing well. So clearly, when we overdo this, we start getting overfitting, and it's the same kind of problem that we saw before. So next week, we're going to take a look a bit more about how to do model selection, regularization, and some more sophisticated techniques than what we saw in the previous lecture. So to sum up, we saw this notion of separability and discriminating between the classes, and we are using linear discriminants. So we have a linear model that we're going to use to separate the two classes. Of course, we not only need to specify this hyperplane, but we also have to know which side belongs to each class. So we use that perpendicular vector. We have that function that is 0 at the discriminant, positive on one side, negative on the other. And if we try to just fit this with least mean squares, we get the wrong result. Because in that case, things that are far away from the discriminant will weigh too much on the function, on the error function, and start shifting the discriminant away from where it can separate the two classes. And now we saw logistic regression as a way to solve this problem. This logistic function gives us a prediction for the probability. So we are trying to approximate as much as possible the probability of belonging to class 1 or class 0 on the different regions of our space. But it also solves this problem of not pulling the discriminant away from the correct position. And we can place the discriminant at the hyperplane where the probability of belonging to one class is the same as the probability of belonging to another class. Now, always using linear discriminants, we can solve the problem of separating linearly separable classes by doing this expansion, nonlinear transformation into higher dimensions, and then using the linear classifier in that space. So to read more about logistic regression, you can take a look at Bishop's book, these sections here. And on the next lecture, we are going to talk a bit about overfitting and how to mitigate the problem of overfitting in classification problems.